Lucid, would you like one of these crackers? I think you'll like them.
How do you know?
It says on the box, no saturated fats. I think those are bad fats.
What does saturated fats mean? I see stuff about fats all over the place. I don't really get it.
I think we need to begin by looking at the difference between saturated and unsaturated fats. Need a little help here?
Hi, I'm Suzanne. If you look at any packet of processed food, you will probably notice fats mentioned on the labels somewhere on the packaging. There are so many here: saturated, polyunsaturated, trans fats. Today we're going to show you what these words actually mean and why they are saturated or unsaturated. But before we do that, we will look at the structure of fats, and to do that, we will get down to the atoms that make them up. Exciting, isn't it? Let's start by taking a closer look at stearic acid. This is stearic acid. This is an example of a saturated fatty acid, an extremely common oil found naturally in animal and vegetable fats such as cocoa and shea butters. For now, let's focus on this long chain, which is an important part of what makes a fat a fat. It has 18 carbons, 17 of which are part of this long chain. The chain is made of carbon and hydrogen. As you probably know, carbon always has 4 bonds, which, if you look here, they all do. Linoleic acid is an unsaturated fatty acid commonly found in a variety of nuts and seeds. Linoleic acid also has a long chain made of carbon and hydrogen, and it also has 18 carbons. Again, carbon always has 4 bonds. There is one major difference, however. At carbon 9 and 12, something special has happened. In 2 places, the carbon bonds with itself in what is called a double bond. When a double bond happens, look at how many hydrogens are attached to each carbon. Hold on to that thought. To really understand saturation, let's take a look at this paper towel. As you can see, it's perfectly dry. And here we have some water. If I pour a little bit of water, as I use the paper towel to soak up the water, then my paper towel really can't do anything more, which means it is now saturated. Now let's get back to our fatty acids. This is stearic acid, and this is basically saturated or soaked up with hydrogen atoms. There's no more hydrogen atoms that can be added to it, and that's why we refer to it as saturated. Going back to our representative unsaturated oil, we notice that it is not full of hydrogens. Wherever there are double bonds, we are missing hydrogens. It is not saturated, and we refer to this type of fatty acid, like linoleic acid, as unsaturated. Now that we have all of that straightened out, let's get back to the chemistry. For carbon, whenever you have a straight chain, which are called alkanes by the way, there is a simple calculation to know how many hydrogens are attached to that carbon. Let's consider this model of hexane. If we count the carbons, there are 6. If we count the hydrogens, we count 14. So, for every 6 carbons in a saturated alkane, we have 14 hydrogens, creating this formula. Okay, let's find out if there are any patterns. Let's do the same thing now for butane, which is another alkane. Here we count 4 carbons and 10 hydrogens. Same pattern, ending up with C4H10. There is a definite relationship being made here, which maybe you have made out. if we refer to the number of carbons as N, the relationship is CN H2N plus 2. Going back to our fatty acids, it seems that every time we had a double bond, we lost 2 hydrogens. Let me do that with hexane and put in one random double bond to do my calculation. This time our formula is C6H12. Just as we suspected, we lost 2 hydrogens. How about that? And for carbon, every time we lose 2 hydrogens, we refer to this as a degree of unsaturation. So, hexane's friend over here, which we call hex-1-ene, has 1 degree of unsaturation. Sometimes, carbons like to make rings, like this one. If we count up the carbons and hydrogens here, we end up with the same thing. We also lose 2 hydrogens. So, what have we noticed? Double bonds and rings can make degrees of unsaturation. And if there is only 1 degree of unsaturation, our general formula is, say it with me, CnH2n. What do you think it is when it's 2 degrees of unsaturation? Oh yay! We made a pattern! And we sound super cool when we talk about chemistry. I hope by now you have a good understanding that unsaturated means that it has double bonds. Unsaturated becomes unsaturated by losing 2 hydrogens for every double bond or by means of a ring. When you lose the hydrogens, that is what we call degrees of unsaturation. On the other hand, saturated fats like stearic acid cannot soak up any more hydrogens, which is why we call them saturated. But now let's get back to these packages and these funky, scary chemistry-like names that they have written all over it, like cis, trans, saturated. What do they mean? When we examine a model of a double bond, we notice that whenever a double bond takes place, the molecule becomes much more fixed in position. If there are long chains on either side, we are either forcing them to be on the same side, like that, or we may have 2 bulky groups on opposite sides. In traditional chemistry, these were referred to as cis and trans, cis being the same side. Notice how I over-enunciate my s to help you remember that cis is same and trans is on the opposite side. Okay, I know I keep talking about the chemistry, but I think what you're really wondering is, why is this important? Well, as you have probably already learned in chemistry, the stronger the intermolecular bonds, the more stable the molecule is, and heavier molecules tend to be more solid or liquid-like. That impacts their melting points. Well, if we're talking about intermolecular bonding, when it's saturated, the molecule can almost curl up on itself and have some lovely London dispersion forces, which makes it really stable. Stearic acid, our old saturated friend, has a melting point of 69.3 degrees Celsius. That means below 69 degrees, it's more like a solid, and above 69 degrees, it's a liquid. Linoleic acid, our old unsaturated friend, which has the same number of carbons, has a melting point of minus 5 degrees Celsius. It melts at much lower temperatures. That means at room temperature, which we scientists seem to like at a cozy 25 degrees Celsius, it would be a liquid. But why? Well, let's look at our models. The saturated compounds we mentioned so far can coil or curve and bond with themselves. But our cis compounds, they have sharp curves or kinks that make things really far apart. With that shape, it doesn't look as easy to curl up with. And in between, we have a trans bond. Although it also adds some rigidity, it still seems to keep the molecule in some basic shape as a saturated version of itself. In general, but not always, the trend for melting points follows this trend. Saturated has a higher boiling point than trans, which in turn has a higher boiling point than cis. As for how this affects our life, it has many health impacts. Although there's more to it in the way of biological interactions, In essence, oily substances do not clog things up as much as solid-like substances. In general terms, cis fats are generally healthier for us, and that is why processed foods often highlight that on their packaging. But do watch for this tricky wording. When you read a label for something that says something like partially hydrogenated, a very healthy oil like soybean oil, what they actually mean is they've added hydrogens to make it more fat or butter-like. Very tricky. Knowing chemistry can save your life. What you should have learned today is that these kinks, or presence or absence of little tiny hydrogen atoms, completely changes the physical structures. That's the difference between saturated and unsaturated. These slight changes in double bonds, which are so slight, change so much. I'm telling you, science, chemistry is full of cool little concepts like these. I hope you learned something. Now, let's get out there and discover some more.
That makes much more sense now.
Oh, so that's how it is.
Thank you for learning with us.